Okay, lesson 69 is direct variation. What's our objective, class? Get ready?
Direct variation.
Good, direct variation. We're going to look at patterns and equations and graphs and some problems for direct variation today. You've actually already done direct variation, you just didn't know it because you didn't call it that. We called it proportionate or directly proportionate. So, direct variation is when you can find one variable by multiplying another variable by a constant. That constant is always called k. What is our constant? Get ready?
K.
K. For example, take a small triangle. If we dilated it and made it larger, we would be multiplying by a scale factor. We called it scale factor, right? But you could also multiply it by a constant, k, to make it twice as big. So take maybe a dimension for x. Maybe it's 2 feet long. If we multiplied it by 3, I could get an output. So maybe the dimension of my new leg in my larger triangle. So really, it's stuff that we've been familiar with before. So k can be a rate, like miles per hour. It can be a scale factor, like the triangle. It could be a multiplier. It could be pages per minute. It could be a slope, like 3/2, or some unchanging number. What are the characteristics? Direct variation is linear. What is it? Get ready?
Linear.
Linear, and it'll go through the origin. What does it go through? Get ready?
Origin.
The origin. In other words, if one variable is 0, the other variable has to be 0. You can see why, right? Because anything times 0 is going to be 0. What do the graphs, or what do the tables look like? And what do the equations look like? So just real quickly, I'm going to just skim through here. Does this match the formula y equals kx? It's close. It has something added on. If I add anything on to this parent formula, or the general formula for direct variation, it's not direct proportion. So our formula has to be in this form. Y equals kx. What's our form? Get ready?
Y equals kx.
Good, y equals kx. So this one is not direct variation. How about this one? It has a power. This is not direct variation because it has an exponent. So be looking for any powers, like 2, 3, or beyond. It's not in this form. How about this one? P equals 4 times s. Is this in the form y equals kx?
Yes.
Yes, it is. In fact, that's like the y. The s is like the x, and the 4 would be my k, or constant. So what does the graph look like? So in this graph, there's a plus 3 here, and what that does is actually gives you a starting value of 3, and your graph just goes from 3. Doesn't go through the origin. Yeah. This one right here has a square. This one actually starts at the origin, but it starts curving because it gets big really fast. This one does go through the origin. If you let s be 0, p would have to be 0. And it's just going to go up 4 over 1, up 4 over 1, up 4 over 1. Or if I let my side length of my square be 1, my perimeter is 4. If my side length is 2, my perimeter is 8. And you can see, linear goes through the origin. So that's what direct variation will be, a line through the origin. Okay, let's talk about variables. Sometimes you'll hear the word independent and dependent variables. What does it mean, and how do you know which is which? I always think of a table. Say this is how many hours I worked at my job. Well, that's going to tell me how much money I can earn, right? But I have to work the hours first, and then I earn the money. I don't know how much money I earn until I've worked the hours. The input is called the independent variable. It can do whatever it wants. I can work 10 hours. I can work 1 hour. Whatever I want. It's independent. What is the x variable? Get ready?
Independent.
Independent. And think of this input, independent. Input, independent. Well, the y variable, I don't know how much money I'm going to get paid. It depends on how many hours I've worked. So the money paid, or the output, depends on the input. So we call it the dependent variable. What is my y variable? Get ready?
Dependent.
Dependent. I like that you're taking notes and writing this down because you're going to see this a lot in high school too. So input is independent, output is dependent. How do you use that? Sometimes in a story problem, you have to know which one to set up in your table as input or output. So that's why that's important. We're going to do some more when we get to lesson 70. Let's look at this. How does this table help us with direct variation? Input, output. What would I times my input by to get my output? And does it follow the same rule every time? Let's see. What would I do to the 2 to get a 4? What do I do to the 1 to get a 2? I like how Kenna's sitting up straight. Her eyes are open. She's listening. Thank you, Kenna. Kenna, what do you think? What's my multiplier? Times by 2. Times by 2. Times by 2. If it's the same every time, that is our constant of proportionality. What is it called? Get ready.
Constant over proportionality.
Good. Constant of proportionality. You can also call it constant of variation. Both works. So if I were to say my output, the output is the input multiplied by 2. Let's write an equation saying that. The output, or I could call it y and x if you're more familiar with y and x. The y is input, or x, times by 2, and I like to put coefficient in front. I just wrote an equation from my table. Is it a direct variation? Yes, because it matches the form y equals kx. And to be proper, I should call x e, and my y is d. And then I could graph it. I'm not going to take the time to graph it right now. Let's do one more. What if we don't have a table and we have to make a table from a given problem? Jared earns $8 an hour helping a painter create a table that shows his pay for 1, 2, 3, and 4 hours of work. So my table, I'm going to have my input. Think of, I've got dollars and hours. Which one happens first? Do I get paid or do I have to do the work, Lucas?
Hours.
Hours goes first. First I work the hours, then I get paid. 1, 2, 3, 4 hours of work. It says $8 an hour, so I know 1 hour of work is $8. How much for 2 hours of work? Get ready?
16.
Excellent. 3 hours? Get ready?
24.
And 4 hours? Get ready?
32.
Awesome. You guys are so paying attention. Thank you. Oh, is it direct variation? In other words, is the constant the same every time? If it's the same every time, then it is direct variation. What is my constant? How would I find it? Tate, you're nodding.
Sorry, what did you say?
Oh, what is my constant? What would I multiply the input by to get the output?
You multiply the input by 8.
Excellent, excellent. Multiply by 8. So my constant of proportionality, k, is 8. What's my equation? Hiram?
It would be y equals 8.
Awesome, awesome. You said the output is found by taking the input timesing it by x. In this case, we could just leave these x and y. Why not? Right? And we keep it x and y. So excellent. Y equals 8x. Then I can say, hey, well, how much would I get paid for 6 hours of work? So I could say, hey, 6 would be what? I could put a 6 right here, right? 8 times 6, that'd be 48. So I'd know, oh, I'd get $48. So that's the cool usefulness of taking a story problem, making a table, finding the k, writing an equation, and then solving a problem. We got lesson 69 next, so just pause right there. So, sorry, we're going to go to lesson 70 now because the two lessons go together. 70 is solving problems. So, let's take this table. What is k? And this camera, video still working, right?
Yes.
How would I find k? Lucas?
You can divide the y, or the price, by the number of CDs sold. So it would be 15 divided by 1, which would be 15. And then you can check it with a couple others to make sure it stays the same.
I like that. You check it with a couple others, make sure it's the same every time. So the output divided by the input, it'll help me find that constant, right? This would be times 15, times 15, times 15, constant proportionality. 15. One quantity, the price, is determined by multiplying the other variable, the number of CDs, by the constant. All right, so that's how we know independent. How much would it cost to get 6 CDs? Let's put it back in there. How much will it cost to purchase 6 CDs? How would I figure that out? Stacia, you're calculating. What are you figuring out?
Well, you do 6
$90. If we wanted to write in our equation, y equals 15x, we put our 6 in for x to tell us our output. So perfect, good. Let's do one more. See, we've talked about all this. We set up an equation. We talked about proportionate. All right, let's talk about a driving one, where we have a rate of change like miles per hour. Driving at a constant speed, the distance Maggie varies directly. Look for this keyword if you see it in your RISE test. As soon as you see there's a direct proportion or varies directly, you know, oh, bing, bing, bingo, or ding, ding, it's y equals kx. That, I know that's going to be my formula. Maggie drives 75 miles in 1.5 hours. How long does it take her to drive 100 miles? So let's make a table. I'm thinking, this is where I have to think. Does time happen first, or does distance driven happen first? Or is it the distance, then the time? And sometimes they seem interchangeable, so I'm going to peek ahead and read. It says use time as the independent variable. So time goes here, hours. This is distance. All right, so it said 1.5 hours for 75 miles. And then it says, how long will it take her to drive 100 miles? How would we set this up and solve? I got 3 hands in there already. They're like, I know what to do. Let's let everyone have a chance to think. How could I find, number one, I need a constant, but I don't see an easy way to find a constant. Okay, Lucas, before his arm rips out of his socket.
So whenever I see this, I think, okay, so 75 to 100 is 3/4, and so 1 point. So yeah, and so 0.5 to.
Okay.
So then you would just solve that.
Wow. No one. I've had different ways to come up with this today, but no one has seen this. Look at this. Reduce this fraction. He made this as a proportion because direct variation relationships are proportionate. Make a proportion. Simplify. Then, hey, double that. I should do that in black. So you would double this to get a 4. So what would x have to be, Jacob?
Well, it'd be 2, but the way you're being something here, I thought, well, 75 miles is 25 from 100, and then they said it was 1.5 to get there, so I'm like, oh, so 25 miles is half of 50, so why can't you just...
Half that number, so it'd be 50, and then do half of that again, add it back on. So you'd say, take some number, half of it, and then add that number back on again. That would be a little trickier, but I see your logic. I see.
I can just picture that and I get the answer in my head. It just pops
That's
up.
pretty good. That's awesome. Hiram.
I have a question. So why would it matter what's independent and dependent? Because it doesn't matter which one's on top if you do it both.
Okay. The only difference would matter is this. That's a great question, Hiram. So let's say I had an equation with the constant of variation is 2. If I were to reverse the variables, it would look like that. That's the only reason why it matters. If you reverse the variables, it's going to switch your constant around. Because in one case you might multiply by something, but if you flipped them, you would be dividing by something.
But isn't 1/2 of x still equal to x? I mean, 1/2 of y is still equal
And
to x.
it still works. Yep, it still works. It just matters, like, if I'm going to read answers tomorrow in the book, it's going to say it like this. Okay? I like these questions. You guys ask really good questions. Okay, did we find everything we needed to? We found our 2, and we found our 2 hours. Okay, good. And we didn't write our equation, but I think you guys got it. Okay, we're in 473. Take a standing break for 20 seconds.
Wait,